Dear students, next topic we are going to discuss is telescope, and we know that the telescope is a device which is used to see very far off objects. So it would magnify the far off objects, and here also we'll use two convex lenses. One is objective lens, which is towards the objective. So in this case, unless last case, in microscope objective was of smaller focal length and eyepiece was of larger focal length, but here objective would be larger or of larger focal length and larger aperture, so that the maximum light should be gathered by this. And so again we are using the technique to make this diagram in the same way. So here also I am going to draw the magnifying this principal axis first. So this is the principal axis, and now you see here the rays would be coming from very far off object, means the object is at infinity. So rays are coming from an object which is lying at infinity. So here we'll draw the parallel beam of light which is incidenting on this objective. So one method here, in as we have discussed, that the objective is of larger focal length and larger aperture as compared to the eyepiece we have to make little smaller. So one tip I'm going to share here, you see the ray may be coming like this way, like very large angle you can make, but it would always be convenient to make a very small angle. A very small angle you need to draw here, so that you can draw the image of smaller size. You see till here, if this is larger, your image would become very larger. It would be larger than the size of this object that we do not want. So here it would be convenient to make this angle very small, so that your image should be somewhere here. Now let us draw this line, the ray. So this ray is coming from infinity. So you can draw the image here. Now another parallel beam of light would be coming. So let us draw the parallel beam of 3 rays. So I have drawn these parallel rays which are coming from infinity, means the object is at infinity. Now we know that when the object is at infinity, image would be formed at the focus of the lens. So we can draw the image here. So all these rays, they would converge at this point. Now small lens we need to draw. So smaller lens we need to draw. From here to here we can draw. The size of the eyepiece should be smaller. This is objective, and you see object is at infinity, so you are getting the image of the object at infinity at the focus of the objective. So this is the focus of the objective, as well as this is the focal length of the objective, as well as the distance of the image from the objective. Now we need to magnify this. So again the same principle we are going to use here. If this image is between the focus and optical center of the eyepiece, so we can consider the focus of the eyepiece is here, so that the image formed is in between the focus and optical center of this eyepiece. So in that case you will get the magnified image. So this lens is basically going to magnify the image formed by the objective lens. So we need that magnification. So in the same way, we are going to draw the magnified image. So first ray I'm going to draw, which is passing through the optical center. So here we will get the virtual image by extending this ray in the backward direction. So these rays can also be drawn. So you can see how I'm drawing the rays. So this would be by the dotted lines. Another rays. So we have shown that all the 4 rays, they are going to meet at this point. So this is the final image we have got of the object which was at infinity. So this is A dash B dash, and this is A double dash B double dash. So this was the eyepiece, and here this is the total ray diagram. So these rays, these are the incident rays on the objective lens which are coming from infinity. So they are going to meet at the focus of the objective, because the object was at infinity. So image would be formed at the focus of the objective. Now the arrangement is in such a way that this image is formed between the focus and optical center of the eyepiece, so that we can get the virtual magnified image of this image which is behaving as an object for the eyepiece. So this is the total ray diagram. So final rays, they are going like this. So this is a total ray diagram when the final image is formed at least distance of distinct vision. So here you are making the arrangements in such a way that the final image is formed at least distance of distinct vision. Now we'll find out the magnifying power of this telescope. So let's find out the magnifying power. Magnifying power as the object is at infinity. So here whenever the object is at infinity, so it would be convenient to use the angular magnification. So angular magnification we are going to find out. So what is angular magnification? So this is basically the angle subtended by the final image over angle subtended by the object at the eyepiece. Now let us see what is the angle subtended by the final image. This is the final image. Let us see in the diagram. This is the final image, and you see this is subtending an angle theta I here. And you see these rays, they're coming from infinity, and these are subtending an angle theta naught with the principal axis at the objective. So if this angle is theta naught, this would also be theta naught, vertically opposite angles. So now you can see we can use theta I and theta naught here, and this would be the common perpendicular for both these triangles. So it would be convenient to find out the magnification. Now as these thetas are very small, so we can use approximation. If theta is very small, theta can be written as tangent theta. So I'm going to write here tan theta I over tan theta O, for as theta I and theta naught are small angles. Now let us find out what is tangent theta I. Tangent theta I is perpendicular over base. So let us consider this is the optical center of eyepiece, and this is the optical center of the objective. So what is tan theta I? So this is perpendicular over this base. So let us write perpendicular over base. So angular magnification is tan theta I. Tan theta I is perpendicular. Perpendicular is a dash b dash over base is a dash ce. So this I have written a dash b dash over a dash ce, perpendicular over base. So similarly we can write theta tangent of theta o. So let us see, perpendicular over this base we will write base is what, a dash co over tan theta o. So perpendicular is same and base is a dash co. So let us simplify and write down the magnifying power. So this AB would be cancelled. So what you will get, a dash C naught over a dash CE. Now let us see what is a dash C naught and what is a dash CE. A dash C naught. A dash C naught. This is what? This is the focal length of the objective. And this is what? This is the object distance of the image from the eyepiece. So let us substitute these values here. This was f naught and this is ue. Now we can use this ue using, let's find out this ue using the lens equation. We know that for the eyepiece 1 over fe is equal to 1 over ve minus 1 over ue. And what is VE? VE is the image formation for the eyepiece, and we know that the image is formed at least distance of distinct vision for the eyepiece. So we can substitute UE, 1 over UE is brought this side, 1 over VE minus 1 over FE. So let us substitute VE. So what is VE here? You can see from here. VE is this, from here this distance. So this is D, and when you're going this side you're going in this way. So VE is minus D. So let us substitute 1 over minus D minus 1 over FE. So this value we can substitute in this expression, 1 over UE here. So let us find out the magnification now. So magnification, angular magnification, it was f naught over ue, and 1 over ue we have obtained as minus 1 over d minus 1 over fe. Let's take this minus out and take this fe also out. So this can be written as, this would become 1 and this would become plus fe over d. So this is what, this is the angular magnification for the telescope when the final image is formed at least distance of distinct vision. So, and you see what is the length of the tube here. One approximation here we will use length of the tube. You see, otherwise this point is very much closer to this. So this UE sometimes can be taken as FE also. So what is the length of the tube? Means the distance between these two lenses. That would be FO plus FE. So length of the tube would be so here with the approximation I'm writing f naught plus fe, that is the focal length of the objective plus focal length of the eyepiece. And here also you are getting minus sign. So this minus sign is showing that we are getting the inverted image. Final image is inverted with respect to the original object which was at infinity. So generally if we are using this telescope as an astronomical telescope for to see the heavenly objects, they are round in shape. So it will not matter whether if we are taking the inverted images. But for the terrestrial objects, another lens is used, which can be used to invert the image, and finally we will get the erect images. Now, the second case is when the final image is formed at infinity, and that is also called normal adjustment of the telescope. So, here in this case, the final image is formed at least distance of distinct vision. So, second case we are going to discuss when the final image is formed at infinity. So, second case is when final image is at infinity, and this adjustment is called normal adjustment. Generally this adjustment is always preferred because here we get less strain on the eye. So if the image formed by the objective is at the focus of the second lens also, then the final image would be at infinity. So let us draw the ray diagram first for this adjustment. This is the objective lens. Now let us draw the principal axis first. This is the principal axis, and as the rays are coming from infinity, so we can draw the rays coming from infinity and keep this angle very small. Now let us see if I want the image to be here. So I'm going to draw two more parallel rays. So these rays, they are coming from infinity. So they will give you the image at the focus of this lens. So we are going to get the real image. So here we are going to get the image. So this is the image A dash, B dash. Now you see this, when the object is at infinity, the image is formed at the focus of this lens. So this lens is the objective lens. So this image is formed at the focus of the objective. So this point is the focus of the objective. Now if this image is also at the focus of the eyepiece. Now let us draw the eyepiece also. Now very fine, very small eyepiece we will get here. Let us draw a small eyepiece. And let us consider this is also at the eyepiece of the focus of the eyepiece. Now let us draw. Now you see this is behaving as an object for this eyepiece, and you see when the object is at the focus of the lens, image is formed at infinity. So let us draw the image at infinity now. So here you see I'm going to draw the ray which is passing through the optical center of the eyepiece. Extend it in the backward direction with the dotted line. Another rays can be drawn in the same way. So all the 3 or 4 rays which we want to draw can be drawn. So these parallel rays, they are showing that the image is formed at infinity. So these rays, they have come from the infinity to give you the image at the focus of the objective, and this image is at the focus of the eyepiece also. So the final image would be formed at infinity. So this is the ray diagram for the normal adjustment. Now in this case, this is a final image. You see these are making angle theta I. So this is the angle made by the image at the eyepiece, and you see this is the angle made by the object. This is same angle. Now in the same way we can find out the magnifying power here also. Let us find out the magnifying power, angular magnification, theta I over theta naught, using the same method, same approximation. Tan theta naught, theta I is what? From here you can tell me what is theta I. So this triangle we can take, if this is CE and this is CO. So what is theta I? Perpendicular over base. Perpendicular is A dash B dash and base is A dash CE. Similarly, we can write this for this triangle, tangent of theta naught perpendicular over base. Perpendicular is again same, A dash B dash over A dash C naught. So what you will get? A dash B dash would get cancelled. So this would go to the numerator, A dash C naught over A dash CE. Now from the diagram we can see what is A dash C naught. A dash C naught is focal length of the objective. So this is the focal length of the objective, and A dash CE is focal length of the eyepiece. So let us substitute both of the values here. Now here you can use directly sign conventions also. You see when you are finding this F naught, you are going in this direction, and when you are finding this for the objective eyepiece, you are going opposite. So F naught can be taken as positive, and A dash C naught CE is taken as negative. Otherwise focal length is not negative, but using the sign conventions to measure the distances, so we have to use this F naught over FE. Negative sign is there because we are getting the inverted image again. So this is the magnifying power of the telescope, F naught over FE, and tube length. Now without any approximation, tube length is F naught plus FE. So this is the tube length of the telescope, and this is the magnifying power of the telescope. Now if you want to, if you want to increase the magnifying power, you have to make the focal length of the eyepiece smaller and focal length of the objective larger. Now if the objective is of very large focal length, what would happen? You see this lens is adjusted in the tube, and only this much portion, if you see, if this is very thick lens for the larger focal length, these edges, it would be very weak to give the support. You cannot hold the lens at the edges only. This heavy lens, suppose if you're using 1 meter focal length or 100 centimeter focal length, this would become very heavy, and these two small edges would be used to give the support, and it would be very difficult to give the support of this heavy lens at the edges. And similarly, for some more limitations would be there. One is the spherical aberrations, chromatic aberrations would be there, and very important is that these edges are very weak to give the support to this heavy lens. To overcome this problem, we use the reflecting type telescope, because in reflecting type telescope, this objective lens is replaced with a concave mirror. And you see, concave mirror only one side of the mirror is used to gather the light, and another side is the painted one. So whole of the back of the mirror can be used to give the support, and it would be free from the spherical aberrations and chromatic aberrations also, and it is very light also. You see, heavy lens would be very costly, and very light mirror, concave mirror, we will be using in the reflecting type telescope. So that would be, that cost of that telescope would be very less. So In order to overcome the limitations of refracting type telescope and to increase its magnifying power, the reflecting type telescope would be used. So that's all for this lecture. Thank you.